First of all, I'm Maria Kolokotroni from Brunel University, London, and I'm going to present today an example of the ventilative cooling, which is in a university seminar room in the UK. As I said, the space is a seminar room. The study system that I'm going to explain has been installed in many rooms in the building, which is a university campus, typically classrooms and offices, but the seminar room was chosen to investigate further because of its use. It is a computer laboratory with higher internal heat gains. I'm now on slide 3. And as it shows here, the climate is temperate maritime with low cooling requirements due to external conditions. So cooling load is mainly determined by the internal heat. A tool that Anna Maria has described earlier was used for an assessment of the ventilative cooling for this climate and this particular building. And as it can be seen from this output, during the summer months of May to September, direct ventilative cooling with minimum or enhanced ventilation rates is suitable for this climate. In slide 5, I am presenting the installed system, which is essentially a demand control ventilation using phase change materials thermal storage to provide cooling. It is controlled by temperature, relative humidity, and carbon dioxide metabolic levels inside the conditioned space, the seminar room in this case. So this schematic on the screen presents the components of the system, and also it indicates the location of the sensors to control its operation. And in the room, as I said, it is relative humidity, CO2, and air temperature. Temperature is controlled by either air drawn from outside or recirculated from the room, depending on the temperature and relative humidity in the conditioned space. And then external is used directly or mixed with the circulated air by passing the PCM thermal storage. If cooling is needed, the air is directed to the PCM storage. If the room exceeds metabolic CO2 concentration limit, fresh air from outside is introduced. So the components of the system is a G4 filter, recirculation damper, a fan, the PCM storage, and diffusers. The PCM storage physical size varies according to its capacity, but for these buildings, it is about 6 by 1 by 0.4 meters. The PCM is encapsulated in an aluminum panel available commercially, and each panel holds 2 kilograms of PCM, which are able to provide 88 watt-hours. And each module of the system studied has 18 panels, and the whole system has 6 modules. The PCM used is a salt hydrate with specific melting, solidifying, and heat capacity characteristics. I'm now moving to slide 5, which presents the refurbished seminar room floor plan that can be seen in the screen. And also the system is shown in the middle of the room. The room has a floor area of 120 square meters and includes 29 desktop computers, so has got a peak occupancy of 299 students. The total maximum internal heat gain is about 60 watts per square meter to include lighting and the computers and everything. The room has got one external wall facing west, and the ventilation and cooling is provided with this 10 kilowatt studded positioned in the middle of the room, expanding ceiling. And here in the photograph, the inlet and outlet are shown as well. Heating is provided through perimeter hot radiators, and the windows are openable. I'm going to the next slide now. and it is not moving. It has moved now, where there is a graph to describe the operation of the system. The amber line is the operational modes, and the system set point is the green dust line, which is, and the rest is the temperature, with the black being the temperature within the room. So we start with the first operation here, midnight to 1 o'clock in the morning, where the fan runs at the highest speed setting for 1 hour to flush the room of stale air. During this time, all temperatures are decreasing. Then we go to the next operation, the summer night charge, from 1 in the morning to 7 in the morning. And during this period, the inlet and outlet temperatures 5 and 7 of PCM storage can be seen to decrease, indicating that the PCM is charged as the external intake air is being passed through them. Then, between 7 and 8 in the morning, the system is switched off before the occupancy. We can see here that the internal temperature in the space increases when the system is switched off, and perhaps in this case it might have been better if something other than a timer is used, not to lose the cooling effect that we have gained during the night. And then the summer mode operation starts. In this room is 8 in the morning until 9 in the evening. In the beginning, we can see between about 8 and 12, the PCM storage is bypassed as the outside air is cooler than room temperature, which is below the set point of 22 degrees. At about 12, the external temperature measured by the external intake T1 reaches the summer set point, and then air is directed through the PCM thermostats to maintain the temperature in the room below the external temperature. The distances between T5 and T7 from 12 until the end of the day, 21, confirm that the PCM is absorbing heat and is delivering cool air into the room, although completely melting must have happened at the end of the day. And finally, the system switches off from about 9 until midnight, and the temperatures here, they seem to be converged to the same value. The system remains switched off until midnight, where the whole process starts again. So we carried out monitoring the building from the system itself, but also additional monitoring. And we used the adaptive thermal comfort approach for the evaluation during the cooling season, as these are the current guidelines for school buildings in the UK and also are followed for non-air conditioned building offices. The upper and the lower limits of the adaptive thermal comfort values are based on category 2. The graph on the screen shows the results during weekdays from 8 in the morning until 9 in the evening for the seminar room for 2 summers. Temperature is the average of all the sensors that we have at 0.5 meters seating people's height. We can see that the temperature did not exceed the upper thermal limit. In general, the low solar gains, because of the small area of the windows and the ground floor position of the room, allow the system to maintain comfortable conditions during the summer periods with full occupancy. For example, during the exams in mid-May and mid-August. However, we can see here that some overcooling occurs for some hours, indicating that night purging might need more detailed control rather than relying on a timer. The CFD plots on the right side of the screen show that at 0.7 meters, thermal discomfort is expected based on the adaptive thermal comfort limits. Of course, there is stratification, but this is with higher temperature, but this is above the seating level. And the air velocity contours show generally a range of 0.1 to 0.2 meters per second within the space, apart from some areas where they are directly under the air inlet. My next slide is about indoor air quality, because the system is a ventilation system as well. And here I'm just showing a graph of the average CO2 levels in the rooms in each month, that it can see that average is quite low, and it has been maintained because below 1000 ppm. There was one instance in the years that we're monitoring that it exceeded 1500 ppm only for 20 minutes. So as a ventilation system for indoor air quality, the system performs quite well. So my summary is that this case study presented a ventilative cooling system. It was a retrofit application in this case, but it can be used in a new build. And as I said, it uses a mechanical ventilation system with PCM thermal storage, which utilizes the night cool air for solidifying the PCM. The system's capacity and control provide indoor air quality, and this is for the external weather conditions of West England. And also the detailed monitoring of the space and the CFD analysis indicated that the system could provide acceptable thermal comfort at occupant level. Thank you.